Welcome everyone to this presentation in this series of doctoral meetings. My name is Antonio. I am in my first year of PhD, and I'm going to talk about my thesis named Closed Loop Flow Control in Turbulent Propulsion Flows. First, I would like to talk about the motivation of this thesis. As you may know, turbulent flows are present in many situations related to the aerospace science, and this is why these turbulent flows are of special interest for us. We would like to control them because they produce a drag force on the surface, and they can have other consequences as affect the mixing inside the gas turbine, or can affect the jet that is being produced. And this is why we would like to control them. How can we do flow control? So we can start from something as simple as proposed changes on the geometry, or even not even on the geometry, but changes on the rugosity on the surface. We have something more complex as passive control. And now we are trying to move towards something even more interesting, active control. It is more complex. We need sensors, actuators, and design a model for this. We would need some power consumption, but in the end we expect to get something even more efficient related to this frame of sustainable development goals, seeking for a more sustainable generation in the aviation industry. First, we need to do this sensing to estimate the velocity in the vicinity of the wall. How can we do it? With a lot of hot wires measuring velocity, perturbating the flow and creating more turbulence. Maybe we need to look for another solution as placing sensors in the wall which can measure pressure, wall shear stress, maybe heat transfer through the wall. Anything that can be related to the velocity could be useful. And here we have a representation of how it would work. Here we have an overview of this thesis, starting with the sensing part. And these figures are from the literature, where what they do is exactly this. With sensors in the wall, they apply some techniques to estimate the velocity field. With techniques as linear techniques and something more complex using machine learning as convolutional neural networks, fully convolutional networks, or GANs. That is what I'm going to talk about later. In the literature, we can find examples doing this in 2 dimensions in predicting parallel planes of velocity, but we are going one step forward in this thesis, trying to do this prediction in 3D. So just with one training, we can represent a full region of volume, and we don't need to go layer by layer. Next, we need to design the control. And for this, we have these 2 techniques that we can find in the literature, also using artificial intelligence, as reinforcement learning and genetic programming. So here we have already the description of our velocity field, and we need to design all the controller system. And next, we need to reduce the model, because from the previous step we have something very complex. And from the original snapshot, we might go through the encoder, as we have here in this example from the literature, to a lower dimensional space, which can be easier to interpret, because the model that we have before is something very complex that we cannot, it's like a black box model, we cannot have a physical interpretation from it. We have neural networks with a lot of layers that have weights with no direct physical meaning that we can interpret. And with this model, we can reduce the dimensionality of the problem and make some interpretation, because in the end, we would like to interpret it and apply it in different applications. And of course, in the end, with this technique, we should be able to recover the original field. Yeah, so after following all these steps, we would get a gray box model that could have some different parameters related to it and could be applied on real applications. And if we need to apply it in something specific, we can tune the parameters and get something that could be applied. Now I would like to make a summary of what I plan to do these years. Now these years I'm doing literature review in different aspects, so all about what is related to this thesis as neural networks for flow sensing, control theory of linear and nonlinear systems, and also for the control techniques. Everything, as you can see, very related to the artificial intelligence field. And also I'm learning and getting familiar with the with the laboratory environment, with the facilities that we have here, and the type of experiments that I expect to do during these years. And also on the part of neural networks and flow sensing, I'm not just doing the literature review, I'm also working on this. And next week I will present a work on a conference about fluid mechanics. Next year I will work on the control of the problem and also the modeling with the mindful identification and trying to make this physical interpretation. And the last part would be an experimental validation. So for that we will need to identify some actuators that we can use in a laboratory environment, select them, and with this design the setups for the experiments that I will do on the third and fourth year, and we plan different applications like axial and swirling jets. And I would like to talk about what I did already about the sensing part. The type of neural network I'm using is a generative adversarial network. We can think of it as an analogy from what happens with fake money. We have two agents here, two networks, the generator and the discriminator. Both of them at the beginning are very bad. The generator makes fake money and the police is not expert, but obviously it knows that it is fake money. So the generator needs to improve its skills, also the police, and at the end both of them are very expert. The generator finally will be very expert on making this fake money, and the discriminator will have also very advanced techniques for that, although it could be confused at some point. So it means that the generator is very good, and this is what we will use here. This would be an example of the generator network that after the training would be very efficient estimating this velocity field. It has as input the sensors from the wall, like wall shear stress or pressure, and it would provide the velocity field. In this representation, it is done in 2 dimensions. The output are planes of velocity, but as I mentioned before, we are doing this in 3D. And here we can see how it is this gap. This is 2 representations of the error. The dots are specific cases of training in 2D at finite wall distances, but we are doing it in 3D and we can cover the whole region at once. As you may expect, it is more demanding in terms of computational resources, but still using a comparable level of training parameters and similar hardware, we can get similar results. As you can see, after some distance from the wall, the error is larger, and it doesn't mean that it is predicting bad. The thing is that it is not predicting, and it is because small scales cannot be predicted accurately from data from the wall for physical reasons, not because the network is doing bad its job. It's because there is a physical reason behind. So we also propose other setups, not studying, as in the second one, not studying so far away, and even in the farthest region we can observe some improvement from the from the original case. And here I have some example of the predictions that we did at different wall distance. We have the originals on top and the predictions on the bottom. As you can see, the most exact ones are close to the wall, but even in the far situation, we can observe the same patterns around structures, although of course it is not exactly, but the main structures are being predicted that are the ones of special interest for control of turbulent flows. And I also have this other representation with a Q criterion that is commonly used to represent this type of structures. We can see both figures similar with some differences, but the same shapes on similar places we can be observed. And that's all from my side. Thank you for your attention, and now I'm open to your questions.